Hello, welcome to the new lecture of integral equations. In the first lecture, we have discussed about the classification of linear integral equations, mainly of two types, Fredholm integral equation and Volterra type integral equations, and the special kinds equations of integral equations of first kind, second kind, and third kind. And now in this lecture we will discuss the one of the application of Leibniz rule for differentiation under the integral sign. Actually we are using this for converting an integral into a single integral which is needed while converting or reducing an integral equation from a differential equation or vice versa. So before talking about the relation between differential equations and integral equations, first of all we will see what is Leibniz rule and its one of the most important application that is needed here. So first of all, let's discuss about the Leibniz rule. Leibniz rule of differentiation. So Leibniz rule. It is actually the derivative of formula for finding the derivative of the integral a of x. The upper limit and lower limit are functions of x, and f is a function of x and another variable, let it be theta. So f of c x theta d theta, and upper and lower limit are a of x and b of x. Suppose we want to find the derivative of this one. Then by Leibniz rule we have the formula as integral a of x to b of x dou by dou x of f of x theta d theta plus f of x comma b of x. F of x comma b of x means in the given function instead of theta we are putting a variable b of x or function b of x into db by dx minus, now the lower limit instead of theta, f of x a of x into dA of x by dx, dA by dx. And let this be equation, there will be some star, and this it is valid if both f and dou f by dou x, if both f and dou f by dou x are continuous functions of both x and theta, are continuous functions of both x and theta. And one more thing, if both a dash of x, that is dA by dx, and b dash of x are also continuous. So this is about the Leibniz rule. Now we will discuss one of its application, which is needed for needed in the reduction of differential equations into integral equations. For that, now consider the differentiation of the function in of x defined by in of x is equal to integral a to x minus theta raised to n minus 1 f of theta d theta, where n is a positive integer and a is a constant. We can number this as equation number 1. So as a application of the Leibniz formula, we are considering one function in of x, which is defined like this, which is an integral of the function x minus theta raised to n minus 1 f of theta. Then we have to find its differentiation by applying the Leibniz rule. So comparing this with the Leibniz rule, we can take the given function. The function to be integrated is f of x theta is x minus theta raised to n minus 1 f of theta. So this is our function. Now we have to find d by dx of in of x, or this is equal to d by dx of integral a to x f of x theta, that is x minus theta in raised to n minus 1 f of theta d theta. Okay. So by Leibniz rule, this is equal to integral a to x dou by dou x of what, x minus theta raised to n minus 1 f of theta into d theta plus f of x d of x. Here we have the upper limit b of x, the function is x, and a of x is a constant function, that is a. So we have a dash of x equal to 0 and b dash of x of db by dx is equal to 1. So here we have f of x b of x, that is x minus theta raised to n minus 1 f of theta into theta equal to what, b of x, at theta equal to x. Instead of theta we have to apply x into b dash x, b dash of x is 1. Now minus f of x a of x, that is x minus theta raised to n minus 1 f of theta at theta equal to a into a dash of x, that is 0. So simplifying this, we will get din of x by d by dx of in of x is equal to integral a to x. Now we have to find the partial derivative of x minus theta raised to n minus 1 f of theta in the variable x. So f of theta can be treated as a constant. Now derivative of x minus theta raised to n minus 1, it is n minus 1 into x minus theta raised to n minus 1 minus 1, that is n minus 2 into f of theta d theta plus the second term x minus theta raised to n minus 1 f of theta. We have to um, substitute theta as x. So we have to replace theta as x. So replacing this, the factor x minus theta will become 0 when theta equal to x. So that term will vanish, and about the third term, that is also 0. So the only remaining is only the first term is there. So this can be written as is equal to n minus 1 into integral a to x minus theta raised to n minus 2 f of theta d theta. This is din of x, d by dx of in of x derivative, or we can write it as d by dx of in of x is equal to n minus 1 into, we know in of x is what, integral a to x minus theta raised to the power is, if it is n here, the power must be n minus 1 into f of theta d theta. Okay. Uh, so here it is, the power is n minus 2. So this can be represented as n minus 1 of x. So n minus 1 into in minus 1 of x, provided n is greater than 1. So if n greater than 1, din of x by d by dx of in of x, derivative of in of x is equal to n minus 1 into in minus 1 of x. Now if n equal to 1, what will be I1 of x? Then by definition I1 of x is integral a to x minus theta raised to 1 minus 1, that will be 0, a to x f of x dx. So d I1 of x, d by dx of I1 of x is equal to d by dx of integral a to x f of x dx. Again applying the Leibniz rule, this will be uh, Mm. So if n equal to 1, this will be f of theta. Sorry, d I1 of x by I1 of x is what? I1 when n is equal to 1, sorry, there is one mistake in the formula, which I wrote. I1 of x is by definition a integral a to x minus theta raised to 1 minus 1, that is 0, that is 1. So into f of theta d theta. So d by dx of I1 of x is d by dx of integral a to x f of theta d theta. So this will be equal to dou by dou x of um, f of theta. Dou by dou x of f of theta means x will be 0. So the integral term will be 0. Now f of x b of x, that will be f of x. F of x into 1 plus b of x, f of a into 0. So this is equal to f of x. That is, we obtained di1 of x by d by dx of I1 of x is equal to f of x. Let this be equation number 2 and this be equation number 3. So this is the first derivative of I1 of x, and we are rewriting the derivative of first derivative of In of x is actually n minus 1 into I n minus 1 of x if n greater than 1. So this was our equation number 2. This is the formula of the derivative. Now d square in by d square by dx square, second derivative of in of x is d by dx of in of x. D by dx of in of x is n minus 1 into I n minus 1 of x by equation number 2. I n minus 1 of x is integral a to x minus theta raised to n minus 2 f of theta d theta by equation number 2. So this is equal to n minus 1 into again derivative of this integral. We have to apply the Leibniz rule. So this will be n minus 2 into integral a to x minus theta raised to n minus 3 f of theta d theta plus um, when we give theta is equal to x, then there is a factor x minus theta. So the second term will be 0. And since the lower limit is a constant, dA by dx will be 0. So the minus third term, that is also 0. So this is equal to n minus 1 into n minus 2 into, now we can write this as I n minus 2 of x provided n greater than 2. So this is our d square by dx square of in of x. Similarly, we can write d cube by dx cube of in of x, third derivative. Third derivative will be n minus 1 into n minus 2 into n minus 3 into I n minus 3 of x provided n greater than 3. So repeating this manner, we can write the kth derivative dk by dx raised to k of in of x is equal to n minus 1 into n minus 2 into etc. into n minus k into in minus k of x provided n greater than k. So in this manner we can write the n minus 1 derivative dx raised to n minus 1 of in of x. So n minus 1 derivative will be n minus 1 into n minus 2 into etc. into n minus um, n minus 2 into n minus 1 into I n minus of n minus 1 of x, or we can rewrite it as n minus 1 into n minus 2 into n minus 3 into etc. into n minus n minus 2, that will be 2 into 1 into I1 of x into I1 of x. That is, this is n minus 1 factorial. So this is equal to n minus 1 factorial into I1 of x. N minus 1th derivative. Therefore, nth derivative d raised to in of d raised to n by dx raised to n of in of x. This is equal to d by dx of n minus 1th derivative. That is n minus 1 factorial into I1 of x, which is equal to n minus 1 factorial into di1 by dx. Now what is di1 by dx? di1 by dx is by equation number 3, it is f of x. So this is equal to n minus 1 factorial into f of x. So the nth derivative of in of x is equal to n minus 1 factorial into f of x. Let this be equation number 4. So this is the nth derivative. Now we may notice some observations. We have in of x is equal to 0 for all n greater than or equal to 1 when x equal to a, or in of a is equal to 0. And one more thing we may notice is that in of x and its first n minus 1 derivatives all will vanish at x equal to a. That means I1 of a, I1 of a equal to I2 of a, all are equal to 0, equal to this equal to in of a. So all this is equal to 0, since the in of x is in the in of x, the integral is integral a to x. So when x becomes a, the integral becomes integral a to a. So that will make to 0. Now the third note is, from equation number 3 we have di1 by dx, or d by dx of I1 of x is equal to f of x. Then integrating this equation from a to x, we have in the left side derivative of I1 of x integrating from a to x. So that will be I1 of x minus I1 of a is equal to integral a to x. Now if the function is f of x, x is now it is the dummy variable, so we can replace it by any dummy variable. So let it be f of, we replace x by x1. So this will be f of x1 dx1, f of x1 dx1. So, and one more thing we know is I1 of a is equal to I1 of a is equal to 0. Therefore, we have I1 of x is equal to integral a to x f of x1 dx1. This is I1 of x. Now, from the equation of the nth derivative of I in equation number 4, we have from equation number 4, equation 4, no? Given n is equal to 2, we have d square of I2 of x by dx square is equal to 2 minus 1 factorial into f of x, or d square I2 of x by dx square, d square by dx square I2 of x is equal to f of x. Again integrating this equation from a to x, we have actually I2, it is second derivative. When we integrate this from a to x, this will become, will move to higher derivative, that is first order derivative. So I2 dash of x minus I2 dash of a, I2 dash of x minus I2 dash of a is equal to integral a to x. Now here it is x is there, so replace that x by x1, f of x1 dx1. Now we know that in and all its n minus 1 n minus 1 derivatives will vanish. So I2 dash of a is equal to 0. Therefore I2 dash of x is equal to integral a to x f of x1 dx1. Again integrating. Again integrating with respect to x from a to x. This will become I2 of x minus I2 of a is equal to integral a to x. Now we were integrating this. Um, so a to x will be given to that one. Then integral a to x to uh, f of x1 dx1. F of x1 then into dx2. So I2 of x minus I2 of a is equal to integral a to x, integral a to x to f of x1 dx1 dx2. Again we have I2 at a is equal to 0. Therefore we have I2 of x equal to integral a to x, integral a to x2 f of x1 dx1 dx2. Or this can also be written as I2 of x is equal to integral a to x, uh, a to x2, I1 of x2, I1 of x2. And we know by definition I2 of x is integral a to x minus theta raised to n minus 1. So that is x minus theta f of theta d theta. This is I2 of x actually. So we have obtained this one. Which one? A2 of x equal to integral a to x integral a to x2 f of x1 dx1 a to x2 f of x1 dx1 dx2, or this is equal to actually I2 of x is equal to 2 minus 1 factorial into integral a to x2 f of x1 dx1 dx2. Now what is I2 of x? By definition I2 of x is this one. So we can write it as integral a to x integral a to x2 f of x1 dx1 dx2. Okay, I2 of x is equal to 2 minus 1 factorial into this one. So this will be equal to, it is 1 by 2 minus 1 factorial means 1 by 1 factorial. I2 of x integral a to x minus theta f of theta d theta. That is 1 by 2 minus 1 factorial. So using this formula we have converted an equation involving two variables x and x2. So this is equal to 1 by 2 minus 1 factorial integral a to x minus theta f of theta d theta. In general we have the result integral a to x integral a to x2 sorry a to xn a to xn minus 1 etc. integral a to x2 f of x1 dx1 dx2 etc. dxn minus 1 dxn is equal to 1 by so here there are n integrals including a to x integral a to x n integrals are taken, so this will be equal to n minus 1 factorial 1 by n minus 1 factorial integral a to x x minus theta raised to n minus 1 f of theta d theta. So this is an important result which will be used for converting differential equations into integral equations. And that time when we integrate twice, we will convert the integrand into twice integral or double integral or triple integral into a single integral by using this relation. So and first in the left side we have integrated the function with from a to x, then integrating this operation n minus 1 additional times, and is often represented symbolically like this in the form or a to x a to integral a to x etc. integral a to x f of x dx dx etc. up to dxn times. So in that way also we can represent this. Okay. So let's